Roots by iterative methods, part Newton-Raphson Formula method. Right. So I derived Newton-Raphson Formula. We're just going to look at how we can use it to find roots to a specific number of decimal places or significant figures. Newton-Raphson's formula says if little r1 is the approximate value of a real root, so again we start from an initial approximation or a guess like we did with bisection last time. So if r1 is the initial approximation of a real root of an equation f of x is equal to 0, then a closer approximation to the root r2, little r2 is given by little r2 is equal to little r1 minus the value of the function at r1 divided by the value of the differential of the function at r1. F dash means the first differential of f. Okay? It should be apparent from that this method can be used on any function that can be differentiated. So, you can only use Newton-Raphson's if you have the skills, ability or information to be able to differentiate the function you're starting with in the first place. Yeah? So, what we're going to do with the quadratic equation we used section. So we're going to compare the methods effectively by doing that. Find the positive root of the equation 5x squared plus 11x minus 17 equal to 0. Have to make an initial estimate to find the R1. So once again, we look for a point where the value of the function changes from negative to positive, because we know then that we've crossed that x-axis and therefore there must be a root between those two. So one method to do it is to sketch a graph. Another method is to look at some values of the function. So this function, when x is equal to 0, has a value of minus 17, negative. We make x equal to 1, it's still negative, value of minus 1. X is equal to 2, a function is worth 25, plus 25. We've got a plus, we've got a negative to positive change. Therefore, there's a root between x is equal to 1 and x is equal to 2. So you can choose either one of those as an initial estimate. Personally, in this case, I'd choose 1 because the result, the function when x is equal to 1 is closer to 0 than it is when x is equal to 2. So you're likely to be starting from a closer point. Okay? You're all happy with that? So initial estimate found in the same way as you did for the bisection method. You need to be careful about guessing. Yeah, because if you... There's the x-axis. It's like that. If you guess if you're looking for that root and you guess too far away from it, you could be over here, the other side of the root. Yeah. Might not be. You might have more than two. Could have three roots. Yeah, just depends how it sits. Okay. If that was a sine function that, or a partial sine function that was fading away, you could have a considerable number of roots, couldn't you? All right. So we start off from finding an initial estimate, like we did for the bisection rule. Okay. Then what we do is the second step is to differentiate that. So what you need now is your table of standard differentials and differentiate the function 5x squared plus 11x minus 17. Right guys, first differential then. How do we differentiate? Yeah. So it's 10x, because it's 2 times 5 and take 1 off the index, plus 11. Yeah? So, sorry? No, that's when you integrate, Lewis. We're differentiating at the moment. We're going the other way. All right? Yeah? So, first iteration. Little r1 is equal to, yeah. The function at r1 is equal to 1 squared plus 11 times 1 minus 17 equals. No, on the page, but we'll put it. It's 21. Yep. Do is by little r2 is equal to little r1 minus f at little r1 over f dash at little r1. At this stage I'm writing it all out so the note back 1 minus yes, and see what you get. So the R2, little r2, the new guess is 1.048, okay, which will be in yeah. When we get that 3 significant figure value the same twice, we stop. Yeah? Second iteration. 1.0472 when. But so how did you round 1.0472 to 1. So we take the and make that R1. Yeah. And what we do then is we've got to do the value of the function. At the new R1. That is 5 times 1.048 squared plus 11 times 1.048 minus 17, whatever that equals. And f dash at the new R1 is equal to 10 times 1.048 plus 11. So we've got a value for the function at little r1. .01952. 0.01952, yeah? I'll go with that. And the value of the first differential at 1.048. Yeah. So new guess is the old guess 1.048 minus the value of the function at the new guess 0.10 equals. We need that to at least 40. So we can run 1.0489, yeah, which rounds to 1.05 to 3 significant figures. Because that value to 3 significant figures and the previous one are exactly the same, we can stop in a similar way to what we did with the bisection method last week. So just check back in your notes from last week, how many iterations did we take using the bisection method to solve that function? So we took 7 iterations last week using the bisection method. Newton-Raphson's method, 2 iterations to solve the same equation. But as we've seen as we've gone through here, the process is similar. We use the change from negative to positive on the function as one way to come up with an initial guess. We then have to find the first differential of the function that we're using. Set our little r1 to our initial guess. Find out the value of the function at that initial guess, the value of the differential at that initial guess, and then use the Newton-Raphson formula to come up with a new guess that's got more significant figures in than we need in the end, which we then round to our next guess of the root, 1.05, 3 significant figures. We then go through that same process again, so we've got a second iteration with our new best guess. Put those figures into the function, first differential, using Newton-Raphson's method to come up with a even closer guess, which in this case rounds to the same value, and therefore you get the same value rounded twice, you stop. Estimate of the root of this function is 1. Last week. Okay, so let's have a look. I'll get you guys to have a look at a function that we looked at last week. Crossing each other. We still need to equate that function to 0. So we have to shift, because we're looking for the point where x plus 3, the straight line, is equal to e to the x. This positive point up here. So you need to equate it to 0. Effectively, you're moving it down. So we're looking for the root on the x-axis. So we've got a function that's equal to 0, and we can make f of x is equal to that function. We then estimate where positive root lies. In this case, we can probably do it from the graph between 1 and 2. But we can confirm that by looking at the result is still positive, but when x is equal to 2, the result goes negative. Cross that x-axis, therefore we must. Yeah. So for a fair test, we'll start with a guess for the root of x is equal to we did when we done the bisection method last week. So off you go. Newton-Raphson's method, and the root of that equation to 3 decimal. We're going to find the roots of the equation f is equal to e comes and for this 2 result to 3 places. You do 4 decimal places to 8. equals who are so 4, 5, 9. Take that. And that rounded figure, Dom, in green, is the same twice. So if you get that same figure rounded on the next 7, 4, 5. Minus 0.9852. Yeah. Value of the differential at that value, minus 4.7311. Yeah. Figures here. We end up with a new best guess of 1.577. Yes, sorry. Times 2. 1.538, which is not yet the same as the previous one. Yeah, so we go on then to a third iteration. This has got to be 1.53, what was it? 77. Put in there. 1.77. R minus 6.2 and differential minus new guess is 5.9, sorry. To 3 decimal places. 6. Yeah. So then we put figure. We end up with a result for the function. Yeah, I'm going to write that differently to that. 0.0033, yeah. And this is minus 3.082. So put those figures in here. This is 1.5. We get a new guess of 1.5052. Rounds to 1.505 decimal places. And when you do the last one, so 1.05552. You get a result here of to the minus 7 and that's 3.5052. What do you get then? Yeah. Just the spreadsheet. Cut along. Push your exponent is. So that's why the numbers are different. Yeah. You come up with the same answer. And this is minus 3.5052, which you know at 2 R2 of 1.505. I got 241. So that was only that last digit that changed, which rounds to 1.505 to 3 dp. So twice stop. Okay? Yeah. Lewis, you started on that one. What guess are you going to start with? Tell me what you've done so far. Thing that you did. Yep. Have you done anything with that function yet? You're not doing, sorry, does that say bisection? We're using NR. Yeah. You haven't, you are using NR, yeah? So tell me what you got on your page. Tell me this hasn't done yet. You've got to equate the function to 0. Yeah, so start again. F of x is equal to 2 ln x plus x minus 2. Yeah. Differential is 1 over x plus 1. What do we do? Yeah, you can't lose that 2. It's a constant multiplier, isn't it? Yeah. Differential of ln x yeah. This is the important thing about Newton-Raphson's. Can you get the differentiation right? Yeah. Otherwise, you aren't going to get the right answer. So off you go and do that now. I'm going to put together a spreadsheet answer so I can show you how that works. All right? Yeah? Spreadsheet method. Right? Are you ready, boys? Wait till you're all looking. Right. Put my headings in. R1 in that column. The value of the function at R1 in the D column. Value differential in there. Calculate the new R2 and round it in the end. Okay? Right. I don't want Microsoft Ink. Go away. Right. In here, I'll put the number 1. That's where we're starting. All right. In that, as the formula for the function, 2 times ln as a function in Excel, brackets, and then that's the cell reference for this number here. C3, take away 2. So that's the function. This cell equals 2 divided by the current value of R1 plus 1. And then in there is your Newton-Raphson's formula. So R1 is the cell C3. The value of the function is the cell D3 divided by the value in E3 gives me a new exact estimate of the root, which I then round to 3 places in the last column. All right? This cell formally in these cells can just be dragged down. Right? Then what you can do, now you've got the formula in this column as well, you can go like that, a foo, and what you're looking for is the same number in this column twice, you got your answer. So, for the assignment question, yeah, use a spreadsheet, but show some hand calculations on how it's done. Alright? Use a spreadsheet to check your answer, but I want you to show me and explain the method. Alright? Did you not? Well, I'll put the video up, and if that don't work, we'll come up with another way. But that's how you do it, alright? Why? I've been told there's a couple of places where that hadn't worked, but most of it has. Yeah. Yeah. Alright? I don't promise. I just do my best, Lewis. Behave yourself.